Okay, thank you again for the wonderful talk. So the second speaker is Fan Yang from University of Pennsylvania.
So shall I start? Okay, great. Thank you very much for organizing this great event. So today I want to talk about the sample canonical correlation coefficients of high-dimensional random vectors. This is a joint work with Professor Zongming Ma at the University of Pennsylvania. Okay, so given two random variables, we all know how to define their correlations. So we can define their correlations by dividing their covariance by the product of standard deviations. However, if we are given two random vectors, we know their covariance matrix can be defined as this matrix as a expectation of X transpose times Y. Then a natural question is how about the correlations? So given a matrix, there are infinite many ways to scale a matrix. So what is the standard way? So the standard way in statistics to scale the covariance matrix is as following. So we define the canonical correlation coefficients by projecting the random vectors X and Y onto different directions given by the unit vectors A and B, and we call this as a correlation between vectors X and Y along directions A and B. Then we find the unit vectors A1 and B1 that maximize this correlation, and we call that such that maximize the correlation as the first canonical correlation coefficient. And then this pair of random variables is called the first pair of canonical variables. Inductively, suppose we have obtained the first k-1 canonical correlation coefficients rho I and the corresponding pairs of canonical random variables. Then we define the next canonical correlation coefficients by finding the directions AK and BK that maximize the correlation along direction AK and BK, but we subject to the constraint that this pair of random variables is uncorrelated with first k pairs of canonical random variables. And we call this correlation as a case canonical correlation coefficient. Okay, so all the previous definition is very lengthy, but there is a very clear present representation of the canonical correlation coefficients defined as following. So the CCC essentially are the eigenvalues of the following matrix, and the matrix is quite intuitively correct because you see this sigma xy is a cross covariance between these two random vectors, while the sigma xx and the sigma yy are the covariance matrices for X and Y respectively. So essentially we are just rescaling, we are just rescaling the cross covariance matrix by these two covariance matrices on the left and on the right, and the CCC are essentially the singular values of this matrix. In the real life, however, we do not know what are the real canonical correlation coefficients. Instead, our goal is to infer the canonical correlation coefficients from the data. Suppose we have n IID samples of the random vectors X and Y, and we form these vectors into two data matrices X and Y. And then a natural candidate for inferring the canonical correlation coefficients is the sample canonical correlation coefficients defined as the eigenvalues of the sample canonical correlation matrix by replacing each matrix with their sample counterpart. So we replace the real covariance matrix with the sample covariance matrix as X. We replace the covariance matrix Y with the sample covariance matrix of Y as YY, and the cross covariance matrix with the sample cross covariance matrix as XY. So it's obvious that the sample canonical correlation coefficients are different from the real canonical correlation coefficients, but we know by law large numbers, when n goes to infinity, they will converge to the real canonical correlation coefficients. However, as we all know, in the modern era of data science, so the assumption n goes to infinity is not so feasible compared to the data dimensions. So we consider a high dimensional setting when the sample ratios P1 divided by n and P2 divided by n does not converge to 0, but to some constant between 0 and 1. And we require this sample ratio smaller than 1 because we want our sample covariance matrix to be invertible. Then in general, there is no way to infer the canonical correlation coefficients from the sample canonical correlation coefficients. But there is a model example for this question. So if we impose some structural assumptions, then the inference is possible. So in the standard signal plus noise model, so we have these two vectors. This Z is a common factor, which is a rank R. The R is usually a small rank. A rank R random vector is ID entries of mean 0 and variance 1 because of this common factor X and Y, they have a non-zero covariance. And the A1 and A2 are just two deterministic matrices. We call it the factor loading matrix. And the epsilon 1 and epsilon 2 are noises with ID entries of mean 0 and variance 1. So this is a standard example for studying these high dimensional sample canonical correlation coefficients. So if there is no signal, in other words, when R equal to 0, the number of signals is equal to 0, then it has been shown that the asymptotic distribution of the sample CCC is given by this deterministic function. It's a nice looking function. Actually, it's very close to the Marchand-Corpuscle law if we disregard this factor 1 minus x. If we disregard this factor 1 minus x, it's actually the Marchand-Corpuscle law. And if you look at the density, is between the h lambda minus and the h lambda plus, and the lambda plus minus is given by these deterministic functions. And as you all know, so in sample covariance matrix, so on the right edge of the Marchand-Corpuscle law, the largest eigenvalue converges to trace with them. This is the same thing also happens for the sample canonical correlation coefficients around the right edge. And here in this figure, there are two dots. Actually, these two dots describe the outliers of the of our signal plus noise model, which we will describe right now. So in a recent paper, suppose all the random vectors are Gaussian random vectors, and the population canonical correlation coefficients are non-trivial. We denote by rho r bigger until rho 1 larger than rho 2 until rho r, and we have r non-zero some canonical correlation coefficients. Then there is a BBP transition behavior in this model also. There is a threshold rho critical defined as this function. If rho I is above the threshold, then the i's sample canonical correlation coefficients converges to a deterministic function depending on rho I and the sample ratios C1 and C2. And if rho I is above threshold, we also know under the scaling n to the 1/2, lambda I centered around rho I actually converges to a centered Gaussian random variable. On the other hand, if rho I is below the threshold, then lambda I converges to the right edge of this spectrum. The lambda I will converges to the right edge of this spectrum, and under the n to the 2/3 scaling, lambda I converges to the trace rhythm. So the proof of this paper depends heavily on the Gaussian assumption. We know for Gaussian, many great things happens. In particular, the eigenmatrix of a Gaussian random matrix is hard distributed on the in the unitary group. Moreover, for Gaussian sample covariance matrix, is the inverse Vishar. We almost know everything about inverse Vishar matrix. If we disregard this Gaussian assumption and consider general distributions, the proof in this paper completely fails. So with a new method, we prove that all the above result actually holds only under the finite S moment assumption, and more precisely, only this CLT will depend on the S moment assumption. All the other results will only depend on force moment. So now let's briefly describe the idea for the proof. As we said before, the Gaussian assumption cannot be used. Instead, we depend on our proof is based on a linearization method. So this is our master equation for the sample canonical correlation coefficients. So this is just as we have learned in linear algebra. By shear complement, this equation is equivalent to the determinant of a 2x2 block matrix equal to 0. Furthermore, applying the shear complement again, this one is equivalent to the determinant of a 4x4 block matrix equal to 0. Now we call this one as a linearization because this matrix depends linearly on x and y, x transpose and y transpose. Now we apply this master equation to our model. We have a signal plus noise, signal plus noise. Then we write the previous master equation into the noise part plus the signal part. We define the inverse of this matrix as the resultant, call it G lambda. Then we pick out this matrix outside this equation. We get another master equation, determinant 1 plus the signal part times the resultant. Now, if let's consider a simple case with only one signal. In this case, A1, A2 are just two scalars, and there is only one non-trivial canonical correlation coefficients given by rho 1. Then this master equation can be written into an even simpler master equation, which is a determinant of the 4x4 matrix. And it depends on this matrix U times G lambda times U transpose, and U is just this matrix. And the main contribution of our work is we show that there exists a 4x4 deterministic matrix such that this random part converges to a deterministic matrix up to a very small error n to the minus 1/2. Now we can write this equation using this local law into the following equation. We have a deterministic matrix plus a small random error. And if we ignore this random error part, then we get a deterministic equation. The solution of that deterministic equation actually is a hat rho 1 is this deterministic function as we have shown before. Now, after adding this small error, as long as this equation is stable, we can conclude that the largest sample canonical correlation coefficients converges to this deterministic function depending on the rho 1, which is a real canonical correlation coefficients, and the sample ratios C1 and C2. So this gives the convergence of the sample CCC to a deterministic value. If we center the sample CCC around this deterministic value, we want to show the CLT. Actually, using this simple Taylor expansion, the CLT of the largest sample CCC actually follows from the CLT of this arrow part. So another contribution of our work is we show this matrix after scaling by square root n actually converges to a Gaussian matrix, which shows the CLT of this eigenvalue lambda of the sample canonical correlation matrix lambda 1. Okay, so that's the idea of our proof, and I want to stop here. Thank you very much for your attention.
So thank you. I think we have time for a question. Anybody wants to jump in? So is I don't know, is it at all maybe it's not worth pursuing, but do you have hopes of removing the 8th moment assumption? Presumably that is completely technical.
We are working on that. The first, right now, I'm not very sure whether it will hold under the, if there is no finite S moment, but I'm pursuing it. I guess it will hold true. It can be relaxed a little bit, but so far we do not know exactly how to do it.
Okay. If there's no other questions, maybe we can set up the next talk. We'll start it in a minute or so.
Can you see this?
Yes, so maybe we can give people a minute or so to stretch a little bit.
Yeah.
Take a sip of water.